Hi there. Today we'll look at group normalization by Yuxin Wu and Kaiming He of Facebook AI Research. So this paper is basically an engineering paper about a new normalization technique called group normalization. So what's the issue here? The issue is that pretty much throughout neural network learning, we're using this technique called batch normalization. Now, batch normalization is a pretty reasonable thing and it works very, very well. So what's the idea behind batch normalization? The idea is if you have data points for machine learning methods and your data is in a 2D coordinate system somewhere down here, right? And you're trying to separate that from the dots, which are here. It is often very beneficial to shift that distribution before you do anything. You want to shift it to the middle of the, basically want to center it, first of all, such that the origin point is in the middle of the data. And then sometimes you also want to do what's called normalize it. And by normalizing, we mean you want to kind of rescale the axis such that things are more or less sort of like Gaussians. So if you look at this distribution, first is the centering, and then second is what is called a normalization. And usually we know that any sort of machine learning methods work better if you do that, and that's mostly in classic machine learning methods with conditioning numbers of the data being better and so on. But if you just want to learn, let's say, a linear classifier, you can see here, you can even save one parameter because you can make it just go through the origin. And that's true in general. So if we draw this in 1D, you'd have a distribution that maybe is very peaky right here. You first center it to the middle of the coordinate system. And sorry about that, it's not really centered. And then you would divide it by its standard deviation such that after it is a unit standard deviation Gaussian, so a normal distribution. The closer your data seems to be to a multivariate normal distribution, the better these machine learning methods work, especially if you look at how signal in deep network is propagating through the layers. So the idea is if it's good for the general machine learning method that the input has a multivariate normal distribution or is normalized, then it's probably good that the input to each layer is normalized. So when you look at how signal features are in between layers, so this is, for example, the conv53. This is a layer somewhere in the middle of a convolutional neural network. And if you look at the spread of how feature signals are throughout training, you'll see that the more training progresses, the larger the kind of spread of features is. So you might get really large numbers or really large negative numbers or maybe really small numbers in your neural networks. And it would be better if you had a layer and the input, you've normalized it, right? And the output then is again a distribution, but it's maybe shifted. That you would first transform that back into a normal distribution before you put it through the next layer. So what batch norm does is at each layer, before each layer, it will do a normalization procedure on the data before giving it to the next layer. And you can do a basically backprop through that. It's also common to learn bias and variance parameter to add after that. But the important thing is that after each layer, the data is normalized such that it is kind of in the most comfortable regime. What's the problem? The problem with this is that you actually need the distribution, right? If you want to center this data up here, you need to know what the data is. So you need to know the entire data. If I want to figure out what is the mean of this distribution, I need all of the data points to decide here's the mean. I need to shift that up to here. If I just have a mini batch like we usually do in machine learning, so if I just have this or this and this and this point, I just have 4 points, I can't determine the mean. But what I can do is I can sort of guess the mean from the 4 points, right? So my guesstimation of the mean would be somewhere here, and that would be usually close enough. And you can also see that the larger your batch is, if you sample at random, the more accurate your mean estimation is going to be. So people have been training neural networks with large batch sizes basically batch sizes have gotten larger and larger in the last year, so that has not been a problem. But what people are doing now is they are doing distributed machine learning, where you do have your data set and you draw a batch, and the batch might be large. So this might be, I don't know, 1 million images. This might still be 4,000 images in your batch. But what they'll do, especially with things like TPUs, is they'll distribute that across many, many, many machines into batches of sometimes as small as 8 samples per unit. And if this is not images, but maybe something longer, like a sequence of text, or if this is a sequence of speech or something like this, you can sometimes even go down to 2 or 1 samples per unit of computation. And of course, you can't do batch normalization. You can't calculate the mean of 1 sample. It's just going to be that 1 sample itself. So either you have 2 options. If you're in small batch sizes, let's say 2, either you take the hit and have your very bad estimate of the mean from just 2 samples or 8 samples, or after each layer you basically do a synchronization step such that everyone communicates to everyone else their statistics, and you can basically aggregate the statistics across the batch. Both are not cool. Usually these frameworks, they don't do this synchronization because it's just too slow. So they'll go with the bad statistics. And you can see this right here in this graph. They have the ImageNet classification error versus batch sizes. So this is a ResNet 50 model trained on the ImageNet dataset using 8 workers, so 8 GPUs. And if they do 32 images per, now just look at the blue line here. If they do 32 images per worker, so it's 8 workers, it's 8 times 32, that's the batch size. That is a large number, 256, maybe. Yeah. All right. So if they do that, then you can see the error is on a state of the art for a ResNet 50. If they go to 16, it's still pretty good. But then as they go lower and lower and lower, so if they go to smaller and smaller batches and spread them out over the workers, then the error starts going up. And this is because the batch norm statistics get worse and worse. So the goal of this paper is to find this group norm thing here. The group norm, this paper claims, is another normalization technique that pretty much does the same thing, this centering and the normalization, the scaling, but it does it without relying on the batch statistics. It basically does it within a data point. And that means that the performance, even though it's a bit smaller at the beginning for this particular example, will stay constant with even in small batch size regimes. So this is potentially applicable, as I said, to things where you have to go to like 2 or 1 sample per worker because it's just the data points, the single data points are just too large. So if you maybe want to train something like BERT on a GPU. So what is group normalization? Group normalization, as I said, works within a sample. Now there have been other methods that work within a sample instead of across the batch, and they tend to not work as well as batch norm. Now this paper here claims that group norm works on par with batch norm for large batch sizes and better than on small batch sizes. So here they have a schematic of what's happening. In batch norm, as you can see here, you have this cube. Now this cube here, n, means the batch size. So these are the data points in your mini batch. This is the thing that is going to get small if you don't have enough memory. Then C would be your channels. So we are talking about convolutional neural networks here, but this is generalizable to other neural networks. The channels are going to be the independent feature maps that you're going to have. So in a convolutional neural network, usually each layer has these things called kernels, and there might be 3 by 3 matrices like this. And if you have an image, the kernel will be slided. This thing right here will be maybe here, will be slided across the image, or slid. Is it slid? Okay, will be slid across the image, and then the numbers in here will be convolved with the pixels, and that will give you the next layer's representation. So whatever the convolution operation is, and you'll slide that over, and that sliding over will give you the values in the next layer. Now you not only have one kernel, but you actually have many kernels. Sorry about this. Let's draw that. So you have more and more kernels. Zip. You have a whole stack of kernels, and how many kernels you have, those are the different kernels are also called your different channels. Now the kernels refer to the weights and the channels refer to the image, but the ith kernel is going to be convolving the ith channel of the image. So at the beginning, the input image has 3 channels, because red, green, and blue. But then the intermediate images can have more channels as you basically as many as you have kernels in the layer right before. Okay, and the H and the W means the height and width of the image. So combined. So the image is kind of unrolled across the height or the width in this direction. So what does batch norm do? Batch norm takes, as you can see here, one channel, and it takes one channel. So maybe this image, this is one channel. Let's just say this is the red channel because I've drawn it in red. It takes that and it calculates the mean 1 over and the standard deviation of that. It calculates those two statistics, and it uses that to do this centering and scaling operation. So all of these methods are going to calculate the mean and the variance and then do the same scaling transformation. The question is just how do you calculate the mean? Batch norm does this across the data points. So it looks at a single feature at a single channel, and it asks, what's the mean across all the data points? What are the data statistics of this channel? And what's the mean and standard deviation? Now, actually, batch norm, I didn't even know that in convolutional layer this works like this. You can also imagine batch norm of really just taking one single feature, and that means of really just taking one of these things right here. So if this goes to the back, and normalizing across that. The important part is that it is in fact normalizing across the data points. So it looks at your batch, looks at the mean and the variance in that batch, and it normalizes by that. I think convolutional layers make sense because you have this invariance in height and width, and therefore, yeah, so that makes sense. But in a fully connected layer, you'd simply you look at one feature at a time. Layer norm is different. Layer norm has basically been proposed as an alternative to batch norm with the same reasoning that this paper has. So layer norm, as you can see here, it does each data point individually. So here we only have one data point that is normalized by itself. So you do this for each data point independently, and therefore it's not dependent on the batch size anymore. But what you'll do is you'll look across all of the channels right here. So all of the channels and all of the width and height. So this entire thing here, this entire thing is basically one channel, right? And then the next channel is here of the image, and the next, no, that's the next image. Well, that is a bad drawing because the image is unrolled. In any case, what you'll do is you look at, so if you have a filter bank like this, you have an image, and the image is composed of multiple channels, right? This is the red, and then you'll have the green, right? This is in the green, and then you'll have the blue channel. And what you'll do is simply you'll calculate the mean across all of the pixels and across all of the channels. You just take this whole NumPy array and you just say dot mean, and that gives you one number. And that's just whatever that number is, you subtract it, and then you say standard deviation and you divide by that. That's layer norm. So an entire layers representation of one image is just normalized to the mean. Now this seems a bit drastic, and that's why instance norm did the exact opposite. They said, wait a minute, instead of normalizing across all of the features, right, we'll go back and do what batch norm does. Batch norm looks at each feature individually. So basically it looks at all of these different axes in the data distribution. It looks at them differently. So if one axis is scaled very widely, we want to normalize that differently than the other axis that is just scaled very shortly. And that's why we'll look at each feature individually like batch norm, but also we only look at one data point at a time. Now, as you can imagine, this doesn't work anymore in a fully connected network. This basically works in a convolutional network where you have a feature map, a channel. So you look at one individual channel and one data point. So that means here you would normalize the red channel individually, you would normalize the green channel individually, and you normalize the blue channel individually. So the image you're going to end up with is simply the red channel subtracted by its own mean and then divided by its own standard deviation. And just within that data point, right? So maybe I should here say across the number of features or something. So I hope that that's clear. So the layer norm drops the dependence on the batch size, but instead says we should normalize across all of the features. And the instance norm says, wait a minute, batch norm had a good idea normalizing only across the features individually because the individual features might have different scales and we should account for that. But also we don't want to be dependent on the batch size. And now this is where group norm comes in. Group norm is basically a mix between layer norm and instance norm. What group norm says, layer norm and instance norm have good ideas. They only go across one sample. They take that. They say, in essence, instance norm has a good idea in that the features should be normalized individually, but it goes sort of too far from it goes too far. You might get not good enough statistics because you're now normalizing each of these things individually. Whereas with layer norm, you're too restricted. You're basically saying that the features, it's fine if the features relative to each other are like this, right? One is maybe very high variance and one is very low variance. Feature norm would keep that, and group norm would say maybe it's not so good. We should normalize the individual features, maybe individually. But their argumentation here is that maybe there are some features that by their nature already have the same sort of scaling and variance. They give an example. If you, for example, have a filter, again, we deal with convolutional layers here, and that filter is a, let's say an edge filter, right? So a horizontal edge filter. So it's very low value here. And let me mark the high value with blue. So this is a horizontal edge filter. If you slide this over a window, and these are high numbers and these are low numbers, it will respond to edges because edges have high, low, high, right? Or vice versa. So it will give you very positive and very negative number every time you slide across an edge. Now you can imagine that in natural images, that filter, whatever image you put in, would, and however you normalize, would give you pretty much the same response as a vertical edge filter. So the horizontal and the vertical edge filter, you'll see whatever their response is, they're probably about equal in size. So we could expect that in a neural network, there will be groups of filters that together exhibit the same scale, and therefore we can normalize across them like in layer norm. So the more things we normalize across, the better statistics we can gather. That's why instance norm doesn't work, because it only normalizes across a very small thing. getting very little statistics. But we should normalize, if we could gather good statistics, we should normalize different features differently. And group norm says, well, since some of the features are almost guaranteed to behave the same, we could normalize across those. Now, of course, you don't know at the beginning which ones those are. So, but you hope that by doing group norm, by basically a priori, so at the beginning of training, you decide what the groups are. And naturally, it's just whichever ones are next to each other. Those are the groups. You'll hope that through the training procedure, basically those groups will learn the features that are equal of size. Well, you basically enforce that. So you kind of constrain the architecture to do that. So that's the idea behind group norm. You basically build these groups of channels, and then you normalize across those, across the groups of, within the groups of channels, across the entire height and width, only in a single data point. And therefore, you gain the advantage of layer norm, of normalizing within a single data point. You retain the advantage of batch norm, of normalizing across single features. And that's what instance norm attempted. But yeah, so you get the best of both worlds, sort of. That's group norm. And now we go and look what it does. So they say, okay, basically all the normalization techniques do this. They subtract the mean and divide by a standard deviation. That's what we saw. And the difference is just across what you collect your statistics. So the group norm is the following code in TensorFlow. As you can see, you simply reshape your data and basically you expand this part right here where you put the extra. So this is C. This entire thing used to be C, and you divide it into group and index within group. And then you just normalize across that and reshape to the original dimension again. And the cool thing is, in batch norm, you have to keep track of these running means, because at test time you sort of don't want the batch statistic to influence anything. You don't have that here. You can just backpropagate through this operation, and you don't need to keep these running averages going and you always care, am I in test or am I in train mode right now? You just do this operation is per data point. So it's just part of your model, right? And they do an experiment where they have 32 images per GPU, so it's reasonably sized, and they can basically show that the group norm and the batch norm, they compare in their performance. Now, I usually don't believe the experiments that you see in single papers, but I think this has been replicated a couple of times now. You see, this is the train error where group norm even behaves a bit better, and then in the validation error it behaves a bit worse, but one could say it is kind of more closely together than the other methods are to the group norm or to each other, these instance norm and layer norm. So at least it's better than instance norm and layer norm. And then once you go into the smaller batch size regime, of course, that's where the group norm starts to shine. So if you go from the 32 images per GPU, which is this low black curve here, all the way to 2 images per GPU, and I believe they could even do 1 image per GPU with group norm, but of course you can't do that with batch norm because you need batch statistics. You can see that the performance of batch norm degrades drastically. Whereas with group norm, this experiment is just funny. They just had to do this, even though you know exactly what turns out. So look at the lines are all exactly in the same place. I mean, come on, like you're just having time to. Probably one of the reviewers was like, "But did you really do the experiment?" They had to put it in. So yeah. So you can see that the batch norm beats the group norm in this setting when you have the larger batch sizes, but the group norm pulls ahead quite drastically when you have the smaller batch sizes. And that is the main advantage. So now you can turn to models that require small batch sizes or small batch per worker. And generally, it's a pain in the ass to just keep track of those statistics for test time. They do verify, which I find pretty cool, that this phenomenon of the responses going apart during training in the internal feature maps, batch norm counteracts that. So with batch norm, you'll get actually a convergence of responses during training. So the more you train, the more normalized basically your internal features will be, and they show that this is exactly the same with group norm. So group norm is, as it seems, it is a replacement. It's not an addition. It doesn't, the gains don't come from different place. It seems to be a substitute for batch norm, though they don't have an experiment where they do both, I believe. Maybe I'm wrong, actually. Maybe they do. But yeah, it seems like you just kind of have to bring some calmness and some standardization into your signal. And how exactly you do that doesn't seem that important, as long as you do it with some precision and some real overall statistics. Yeah. What I don't like about this is now you have, of course, a new hyperparameter, which is this number of groups, right? So that seems rather annoying, and the gains like this usually come from the introductions of new hyperparameters, and that just it's not that ideal for a method to introduce a new hyperparameter. At least layer norm and instance norm didn't. And now, as you can see, the number of groups is not super influential, but does have a bit of an influence on the performance. So if you go number of groups, or here number of channels per group, of course these two numbers are inversely related. The more groups you have, the less number of channels per group you have. If you go to one extreme, you will get to the layer norm, basically. So the layer norm is an extreme case of group norm, where you just have one group. All the channels are in the same group. Then the performance, as you can see here, is quite a bit worse. If you go to the other extreme, where every channel is its own group, that's equivalent to instance norm, again, the performance is quite bad. And somewhere in the middle, here with 32 groups, seems to be a good sweet spot. So I don't like the hyperparameter. Seems to be somewhat of a thing where you really have to hit a good value. And I guess we'll see over time if that value is always going to be about the same, like the beta 2 of Adam. It's always like, people never change it from 0.999 because it just tends to work, or whether that's really going to be another hyperparameter to fit. That seems to be annoying. They do a bunch of ablation studies and tests on, as we said, for example, object detection and segmentation. So models where you must go almost to small batch sizes just because. So video classification. So if you want to classify an entire video, that's a lot of data, right? And you almost have to go small batch sizes for that. They do a lot of experiments, and generally, as I said, I believe these results for group norm have been replicated across the community a bunch of times now. And I would definitely consider group norm if you are thinking of especially a distributed machine learning project. All right, with that, I hope you enjoyed this paper. I've been talking for way too long now. I wish you a nice day. If you haven't already, please subscribe, like, share, comment, whatever you feel like doing. Bye-bye.